Today we are going to talk about probably the most difficult subject in mechanics, which is motion of a rigid body. By definition, a rigid body is a body without any deformation. And that means that the distance between any two points in the body does not change in time. For example, we have here a body, and we have 2 points A and B here. And what I'm saying that no matter what's happening with this body, no matter how it moves, the distance between these 2 points is going to stay constant in time. So what we're going to do now, in addition to these 2 points, we're going to introduce a third point O, which is going to be a stationary point in the point of this body. Now we can connect these 3 points with vectors and write the relationship between those vectors. The next thing we're going to do, we're going to differentiate these vectors with respect to time, both right-hand side and left-hand side. And that gives us the relationship between the velocities. We see that velocity of point B with respect to a stationary point is equal to velocity of point A with respect to stationary point plus the velocity of point B with respect to point A. But since this is a rigid body, the distance between the point A and point B does not change in time, which means that the only thing that point B can do with respect to motion to the point A is to move in a circle centered around point A. This is true for two-dimensional motion. In three-dimensional motion, we're going to have a similar thing. The only thing different is the point B will be moving somewhere on a sphere around the point A. But this means that the point B cannot translate, but can only rotate around the point A. So that the motion of any point actually on a rigid body with respect to a stationary point could be actually split into translational motion of one point, in this case point A, and the rotational motion with respect to this point. We can write rotation as a vector product of the angular velocity and the vector AB. If you're not familiar with vector product, don't worry about it. It's not that important right now. It's sufficient to understand that rotational velocity is a tangent to the circle at point B. And also it is at 90 degrees to the vector AB, to the radius. And the magnitude of this velocity is actually equal to magnitude of angular velocity times the distance from point A to point B. So now let's pick up some other point C on the rigid body. In a similar way, like we did for point B, we can write the velocity of point C as velocity of point A with respect to stationary point plus rotation of point C around point A. And notice that omega here is the same as omega here. So angular velocity of any point with respect to point A is the same. And that's because if it was something different, if we assume that angular velocity for point B is 1, for point C is another value, well, we find that in time the distance between point B and point C is going to change. And that is not allowed for a rigid body. The next thing, let's pick up a point A prime instead of point A. Now we can consider, in a similar way as before, the velocity of point B as velocity of point A prime with respect to the stationary point plus rotation of point B with respect to point A prime. And again, in this case, angular velocity is the same as in the previous case. So essentially there's always just one angular velocity regardless of what points you're going to look at. Now let's consider a problem of a wheel rolling without slipping. And that means that that point D at the bottom of the wheel, that point D that touches the ground, has to move with the velocity of the ground, which is 0. And now we can represent the velocity of any point on this wheel, including the point C, the center of the wheel, through the velocity of point D and the velocity of the rotation of point C with respect to point D. In this case, choice of point D is very good because velocity there is 0, and that means the first term on the right-hand side is just going to go away. And the formula for the velocity of point C simplifies as a pure rotation. Since we normally know the velocity of point C and we know the speed at this point, we can use this expression, more or less scalar expression, like this, to calculate angular velocity. Here I denoted the distance from point D to point C as r, because this is actually a radius of the wheel. And also we can see that the motion of point C with respect to point D is clockwise. In a similar manner, if you pick up some other point, say point B, we can calculate velocity of point B as velocity of point D plus rotation of point B with respect to point D. And in this case, we know the velocity of point D is 0. And the rotation of point B with respect to point D, it can be represented in magnitude by this expression as angular velocity, which we calculated here, times the distance from point D to point B. The direction of this vector should be at 90 degrees to the segment BD, and also it should be in the direction which makes the wheel rotate clockwise. So now let's ask ourselves the next question. What about acceleration? Well, we can take this equation for velocity of point B and differentiate it with respect to time. In this case, we get an expression for acceleration of point B with respect to point D. So this acceleration will be acceleration of point D with respect to the ground plus acceleration of point B with respect to point D. Now, and here we have a problem. Because although velocity of point D was 0, acceleration of point D is not 0. Because notice, point D is a point on the wheel. So when wheel moves and rotates, the point D is gonna move and rotate. So currently point D is right here, velocity of it is 0. Then point D is gonna be here, here, here. It's gonna move on the edge of this wheel. And when the point D is not at the very bottom but somewhere else, there is non-zero velocity of this point, and therefore it will be non-zero acceleration of point D. And therefore it's very hard to apply this formula because we can't easily calculate acceleration of point D. So instead of using point D, we should look at this wheel more carefully and see, is there any other point velocity of which and acceleration of which we know? And the answer is yes. We normally know velocity and acceleration of point C, center of the wheel. Therefore, it would be more convenient to express acceleration of point B through acceleration of point C. Now let's consider a simple case when velocity of point C is constant. In this case, acceleration of point C is 0. And that means that acceleration of point B is simply acceleration of point B with respect to point C. But how does point B move with respect to point C? Point C is the point on the rigid body. Well, point B, like in any point on this wheel, is going to be rotating with respect to point C. Now it's going to be rotating with constant angular velocity based on these formulas, because we assume that VC is constant. And that means if you're looking at point B from perspective of point C, point B rotates around point C, moves in a circle with constant angular velocity, which means with constant speed. And we know that the point that moves in a circle with constant speed is moving with centripetal acceleration, which means that acceleration of point B will be pointing toward the center of the circle, towards the point C. And the magnitude of this acceleration will be described by this formula. It's angular velocity squared times the distance from point C to point B. And this is it for today. Next time we're going to talk about dynamics of the rigid body motion. See you then.